Spheres. Spheres are hard. Well, they're hard to visualize, but once we get them done, they're easy. Okay. On your left side, figure 1 are your, what kind of coordinates are these? Right? So yes, Cartesian definitely, but these look like cylindrical coordinates because these will form cylinders, right? Now, figure 2 here represents, see the difference?
Yes.
Okay, be very certain that you see the difference between them. The R for your spherical coordinates is a point in space. So I want you to do me a favor on your coordinate axes, write 2, 1, 3. So visualize where 2, 1, 3 would be. Okay, now see what coordinates you're going to need in order to make it into a sphere. So let's do a cylinder first. So what do you have to do to this point in order for it to be a cylinder? Right? Now, what do you have to do in order for this to become a sphere?
Rotate it like every way.
So rotate it every which way possible, right? You have to rotate it in a circle and in a round, right? So literally what you will have is this kind of a thing where you have to rotate it down and you have to sweep every single circle. So you have to do all the way around, right? Which makes it really, really complicated. So because it's so complicated, instead of thinking about doing that, what we're going to do is we are going to do what is called a projection onto the XY plane at the bottom. So remember when we projected this one down? I'm going to do this, right? This was also a projection down, right? But this was a simple projection. It just projected and went around. Yes? In this case, it's going to be a little bit more complicated because when you project this one down, there is actually going to be an angle that exists. There was no angle in the straight one down, but in this case, there's an angle theta to account for. And that angle theta is this angle coming down, or in fact, from your angle, it'll be this angle coming down. Do you guys want to see this? So this is that angle coming down. So in your spherical coordinates, if you have a point that's right here, so I'm going to use this now. If I have a point that's right here, look at where my arrow is pointing. It's coming down that way. Do you see my delta? My delta element? Do you see the delta element coming down? So that makes it complicated. So instead of just a simple projection, that projection itself will have angles. So for example, if I look at this projection, this projection, when we were doing it here, were just R, because that's all it was. However, in this case, it is actually dependent on the angle theta, the polar angle. So that projection, pick a color. Pink. Instead, this is going to be R sine theta. Why is it R sine theta? Because look at it where it comes from. Do you see where it comes from? This is what? R cosine theta. And this is R sine theta. Do you see it? So in fact, you are projecting down R sine theta. Clear? So think about it in this case. This was your angle that was, imagine this is sitting in here, right? This is sitting in here. This is your angle. The angle goes this way. Remember our sweeping angle was phi, and then we did a d phi. This angle is theta, and we're going to do d theta, right? So this little projection that gets shown, guys, look up, look up, look up, don't look down. Do you guys see that? This angle right here is theta coming down, and that little angle sweeping is d theta coming down. We will still have our regular r's and phi's down here, but that's a new angle that we are introducing in. Just visualize that your theta goes down that way, and your d theta is that little element that goes down that way. We still have our original r's and phi's. Those still exist. Does that make sense? So now that we've established that, the rest of it is going to be easy. Do you see where the r sines and the r cosines come from? Yes? So we're not just projecting r onto another r. We are actually projecting r sine theta onto our system, right? So we are still going to be sweeping and doing all of these other things, right? But it's going to look like that.
Okay. That's nifty. Okay.
Yes. Okay. So now this is going to make sense. Hopefully. We will figure this out. I promise we will figure this out. So if I was to do the area element, which just includes this part, I have to talk about the projection of this. So remember, we're talking about the projection. This would be r sine theta. Yes?
Yeah. That red highlighted portion, is that supposed to be like on the surface of the sphere?
Yes. Yes. So we're just doing the surface right now. Does this make sense why this is r sine theta? And we are talking about what? The sweep. So what should go with this? Got it? So in this case, our sweep that was just r d phi before is going to be r sine theta d phi. That's the hardest thing to understand. Do we understand that? Good. Okay, excellent. So remember, this r d phi has now become r sine theta d phi. Yes? And then in order for all of the circles to be accounted for, we have to do, for every single one, our area element will be r d theta, r sine theta d phi. Why r d theta? Because r is what defines where d theta exists. Okay, so if you have a surface only, we're talking about just the surface, and this angle changes, what defines where this d theta should exist? R defines it. Got it? It has to be at the R because we're talking about an empty shell. How many integrations should I have? Somebody said 2, somebody said 3. How many do you think? Is there a DR? So how many should we have? Got it. Okay, integrations over what and what? R squared is common out, sine theta, d theta, and d phi. Limits for the sweep, always. And for theta, the limit should be 0 to pi, always, right? If you have a semicircle, you go all the way around, you go through pi, it becomes another circle, right? Okay, anyone remember what the integration of sine of theta is?
Negative to cosine.
Good. And cosine will be, so this will be r squared minus cosine of pi. Anyone remember what cosine of pi is? Isn't it minus 1?
Yeah. Is it sine of 1?
Yep. So minus 1. And then it's r squared 2 pi. So minuses cancel out, right? Minus 1 is minus 2, and then minus goes away. Just making sure we're all on the same page. So the area of a spherical shell is 4 pi r squared. Woohoo! So simple.